Let me begin with something that sounds almost insulting in its simplicity. We already have computers. They fit in our pockets. They guide airplanes, perform surgery, land rockets, stream movies, and let us argue with strangers across the planet. So when someone says, "We're building a quantum computer," it sounds like they're just building a faster one. Bigger, stronger, smarter. But that's not what's happening at all. A quantum computer is not just a better version of your laptop. It's more like trying to build a machine out of mist, out of shadows, out of something that refuses to sit still long enough to be used. And that's where the nightmare begins. You see, the ordinary computer works because the world at our scale behaves nicely. You flip a switch, it stays flipped. A wire carries current or it doesn't. It's either on or off, clear, stable, reliable.
We begin with something that sounds almost insulting in its simplicity. We already have computers. They fit in our pockets. They guide airplanes, perform surgery, land rockets, stream movies, and let us argue with strangers across the planet. So when someone says we're building a quantum computer, it sounds like they're just building a faster one. Bigger, stronger, smarter. But that's not what's happening at all. A quantum computer is not just a better version of your laptop. A quantum computer is not just a better version of your laptop. It's more like trying to build a machine out of mist, out of shadows, out of something that refuses to sit still long enough to be used. And that's where the nightmare begins. You see, the ordinary computer works because the world at our scale behaves nicely. You flip a switch, it stays flipped. A wire carries current or it doesn't. It's either on or off, 1 or 0, yes or no, clear, stable, reliable. That reliability is the entire reason modern civilization exists. Your phone works because tiny switches inside it, billions of them, are incredibly obedient. They sit there quietly, holding their state like disciplined soldiers. But now imagine building a machine out of particles so small that they do not behave like soldiers at all. They behave like dreams. Quantum particles do not like to commit. They don't want to be simply on or off. They want to be both at once. They want to be here and there. They want to exist in possibilities rather than facts. And that sounds poetic. It sounds magical. It sounds powerful. And it is. But it's also terrifying if you're trying to build something practical. Because how do you construct a reliable machine out of something that refuses to choose? Let's think about it in everyday terms. Suppose you're trying to build a house out of bricks. Easy enough. Bricks are solid. They stay where you put them. Now imagine your bricks are made of smoke. When you try to stack them, they spread. When you touch them, they swirl. When the wind blows, they disappear. That is what it feels like to engineers trying to build a quantum computer. The fundamental unit of a normal computer is a bit. A bit is like a light switch. On or off. 1 or 0. The fundamental unit of a quantum computer is something stranger. It can be on and off at the same time. Until you look at it, the moment you check it, it suddenly decides. Imagine a coin spinning in the air. While it spins, you could say it's both heads and tails. While it spins, you could say it's both heads and tails. But the instant it lands, it must choose. Quantum systems live in that spinning moment. Now here's the nightmare. That spinning moment is incredibly fragile. If the coin hits the ground, it collapses. If the coin hits the ground, it collapses. If someone bumps the table, it collapses. If air resistance slows it, it collapses. And in the quantum world, almost everything is a bump. Heat is a bump. Light is a bump. Stray radio waves are bumps. Even the mere act of existing in a warm room is a bump. Quantum computers must be kept colder than outer space, not because scientists enjoy showing off, but because warmth is chaos. Warmth means atoms are shaking, and those shakes disturb the delicate spinning coin of quantum information. Think about that. To build this revolutionary machine, we first have to silence the universe. We must freeze it, shield it, hide it from the world, because the quantum state is like a whisper in a hurricane. And that's only the first problem. There's another strange feature of quantum systems. They can become linked in a way that defies common sense. Two particles can become so deeply connected that changing one affects the other, even if they are far apart. That sounds like science fiction, but experiments show it's real. For quantum computing, this linking is the whole point. It's the magic. It allows certain calculations to be done in ways classical computers cannot match. If linking two quantum bits is like getting two soap bubbles to merge without popping, then linking hundreds or thousands is like trying to build a cathedral out of soap bubbles in a windstorm. Every extra quantum bit increases the fragility. Every connection multiplies the risk. Errors creep in constantly. Tiny disturbances twist the state. Information leaks away. And, unlike classical bits, which are sturdy, quantum bits forget easily. It's as if you're trying to write a novel in sand while the tide keeps rising. Engineers have developed clever ways to correct errors, but correcting errors in quantum systems is not like ordinary error correction. You can't simply check the value and fix it, because checking it collapses it. Imagine proofreading a sentence that disappears the moment you read it. That's the kind of paradox we're dealing with. So we invent indirect methods. We watch patterns around the system rather than looking at it directly. We infer, we protect, we dance around the truth rather than grabbing it. And that dance is unbelievably complicated. People sometimes ask, why is it taking so long? Why aren't quantum computers everywhere yet? Because nature is not cooperative at that scale. At the human scale, the world feels solid, determined, predictable. At the quantum scale, reality feels more like a rumor. It's not that it's random in a sloppy way, it's random in a deep structural way. The uncertainty is built into the fabric of existence. And here's where it becomes philosophical. The reason quantum computers are hard to build is not just engineering difficulty. It's not just funding. It's not just material science. It's because reality itself does not want to be pinned down. We evolved in a world of rocks and trees and falling apples. Our intuition is shaped by solid things. But at the base of everything, under the rocks, under the trees, under your own body, the universe is made of something slippery, something that resists being fully known. And yet, we are trying to build a machine out of it. There's something beautifully human about that. We discovered that the world behaves strangely at small scales. We didn't invent that weirdness. It was forced upon us by experiment. We had to accept that particles can be waves, that possibilities can interfere, that observation matters. And instead of saying that's too strange, let's ignore it, we said. Can we use it? That's audacious. It's like discovering that water flows downhill and then deciding to build a hydroelectric dam. Only this time, the water sometimes flows sideways and occasionally evaporates when you look at it. Now, there's another layer to this nightmare: scaling. It's one thing to control a few quantum bits in a lab. Scientists have done that. It's impressive. It's delicate. It requires extreme cooling and careful isolation. But to make a useful quantum computer, you may need thousands or millions of these bits working together with very low error. Think about the difference between balancing one spinning plate on a stick and balancing a million spinning plates, all connected by invisible threads. One wobble can cascade. One tiny imperfection in the material can ruin coherence. Even cosmic rays from space, tiny particles constantly hitting Earth, can disturb the system. So some labs build their devices underground to reduce interference. Think about that image. To compute, we hide beneath the Earth, inside refrigerators colder than space, shielding our fragile quantum whispers from the universe's noise. It sounds almost mythical, but it's just physics. The nightmare isn't because scientists are incompetent. It's because the quantum world is exquisitely sensitive. And maybe that sensitivity is telling us something deeper. At our scale, we think of information as robust. You can write it on paper, carve it into stone, store it on a hard drive. At the smallest scale, information is intertwined with existence itself. To store it is to maintain a pattern of possibility against the restless shaking of the cosmos. It's like holding a soap bubble in a thunderstorm and insisting that it remain perfectly spherical. And yet we try. Why? Because if we succeed, certain problems that are practically impossible today might become manageable. Problems involving complex molecules, materials, encryption, optimization. We don't fully know what doors will open. That uncertainty is part of the adventure. But here's the most important thing to understand. The difficulty of building quantum computers is not a sign that the idea is flawed. It's a sign that we are brushing against the fundamental rules of reality. Every time a quantum bit loses its delicate state, it reminds us, you are working at the boundary of what can exist coherently in this universe. It's humbling, and it's inspiring. because it forces us to confront how strange the world really is. You and I feel solid. B, UT, inside us are particles in constant quantum motion. The stability we experience is an emergent illusion, a large-scale pattern arising from microscopic chaos. Quantum computing attempts to stop hiding from that chaos. It says, let's operate directly in the storm, and storms are not easy places to build machines. So the nightmare is real. The fragility is real. The engineering challenges are enormous. But the deeper lesson is this. The universe is more subtle than our everyday thinking allows. The fact that it's hard means we are asking deep questions. We are trying to harness not just electricity or mechanics, but possibility itself. And maybe that's the most poetic thing of all. We are attempting to compute with the raw ambiguity of existence. So next time you hear about quantum computers, don't imagine a sleek, futuristic laptop. Imagine scientists whispering to spinning coins in the dark. Imagine engineers trying to freeze chaos into obedience. Imagine humanity daring to build a machine out of uncertainty. And ask yourself this. If reality at its core is built from possibilities rather than certainties, what does that say about us? About choice? About knowledge? About the limits of control? Perhaps the nightmare is not just technical. Perhaps it's philosophical. Because to build a quantum computer, we must accept that certainty is not the default state of the universe. Possibility is. And that idea, once truly understood, changes everything. We are not just constructing a new kind of computer, we are learning how to dance with the deepest structure of reality. And that dance is difficult. It is delicate. It is terrifying. It is beautiful. And it has only just begun.